What's up?
Yes, Karthik.
So you can share your PPT. Thanks, sir. Thanks for it's room is yours and you can share your things. So
All right. I have shared my screen.
okay, we are able to see it, sir.
All right. Okay. So can I start now then?
Sure, sir. Participants, we are starting a class. Thank you, sir.
All right. Thank you. All right. Good afternoon, everyone. My name is Dr. Awad, and well, I think you've seen some of my introduction, but I will basically talk bit on the energy needs for the future and how we can work on making the students ready for that, right? So I'm going to talk about two things which I'm passionate about: energy and teaching. And I'm glad to be given this opportunity to talk today. So let's just go over quickly uh, the presentation outline. I think there's some problem with my camera, so it's kind of switching on and off. So let's leave that. First of all, can everyone hear me? Is my voice clear?
Yes, sir. Your voice is clear and your
Okay.
presentation is also audible. Participant is his voice clear? Participants, you can speak out.
Yes, Karthik, it's audible. It's good. It's pretty good.
Yeah.
Yes, it's
Thank you.
clear,
Thank you,
clear,
sir.
it's clear.
Thank you, sir.
Okay,
Thank you
great.
so much, sir.
Thank
Thank you
you.
so much.
So the way I want to deliver this talk is that I'm going to start with a brief description of my academic journey. Then we'll focus more on the energy aspect. We'll talk about what is the current status of energy, what does the future of energy look like, and then I'll share some of the new teaching methods that I have implemented here at KFUPM, and also the ones which are being generally used worldwide to improve student retention and improve course learning outcomes. So, so I started with my bachelor's in mechanical engineering in NIT Warangal back in 2009, and after completing my bachelor's, I moved over to King Fahd University of Petroleum and Minerals (KFUPM) in Saudi Arabia to pursue my master's. This was more of a master's in simulations with focus on developing energy storage solutions for solar thermal uh, systems, and this was done with collaboration with MIT researchers. So we did that, and I sort of completed my master's in 2 years, and I moved on next to my PhD, which I did in KAUST, King Abdullah University of Science and Technology in Saudi Arabia again, on the other coast though. During my PhD, my focus was mainly on experimental techniques. I developed a lot of new laser sensors and studied the fuel chemistry. With the energy in mind, we are looking up different, let's say, alternate fuels, as well as we're looking at ways to improve the combustion efficiency in different energy conversion devices such as engines, gas turbines, and so on. So again, it was something related to energy, although it was related to, let's say, the conventional form of energy, whereas in master's it was more on solar energy. After completing my PhD, I went over to Germany to RWTH Aachen University, and specifically to the Institute for Combustion Technology, where I worked on a nationwide project to identify the alternate fuels, the fuels which could create from excess renewable electricity and combining that with the CO2 from the atmosphere. So these were what is called as sustainable fuels. And I think a part of my introduction that you just heard before my talk today, it deals about the work that I did there. After that, I joined KFUPM for my as an assistant professor in mechanical engineering 2 years back. So this is a brief overview of the research that I've generally been involved in pictures to give you an overview of what I've worked on. So this is me working on a laser sensor in cows. So I developed a very sensitive laser sensor to detect ethylene up to parts per billion levels. The idea was again to improve the way combustion happens in engines, and we were creating very sensitive sensors which would allow us to achieve our objective. I also worked on developing other systems such as a low pressure flame chamber and a mass spectrometer. The mass spectrometer is shown here. The low pressure chamber is shown here on this in this figure on the left, and this again were done to sort of study the new regimes of combustion. How does electric field improve combustion efficiency and so on? Again, with the overall objective of trying to improve the thermal efficiency of gas turbines in power plants, and as well as the gas turbines for aircraft propulsion. After that, I went to Germany and worked on the sustainable fuels, and this was the experimental setup along with the gas chromatograph that I had to use. So the idea again was to identify out of maybe thousands of potential fuels, identify certain 10 to 20 fuels which would make sense from combustion point of view, and take them for further testing in engines. So the idea was to look at their chemistry and see which one makes sense and which one don't. All right, so this is sort of the overview of the research that I've done over the past decade, and it has been more or less dealing with the energy, all the different aspects of energy, right? In my master's, it was solar. In my PhD in postdoc, it was more about combustion, and it was about either using fossil fuels or maybe renewable fuels to meet our energy needs. So let me start off by giving you an overall status of the current energy system that we are living in and how it's going to change in the future, right? So this is really important for us to understand the transition that we're going through to be able to teach our kids on what needs to be done and what opportunities do they have, right, in the next, let's say, 10 to 20 years time frame. So if you look at the world energy demand by fuel, these are the pie charts showing the share of different fuels that meet the energy demand. The one at the top shows the situation for 2030, 2013, and the one at the bottom shows it for 2040. Of course, the one for 2040 at the bottom is a predicted one. The values would change a bit here and there, but that's the direction in which we're going overall. So how does it look like? Well, if you focus on the 2013 pie chart, we can see that coal, oil, and gas are contributing to more than 80% of our energy needs. That's where almost all our energy needs are being met from, right? There is, of course, a small share of bioenergy in terms of biofuels. There's 3% coming from hydro, 5% from nuclear, but these are all pretty small parts of the pie. There is 1% renewables, although back in 2013, the percentage of renewables was pretty small. Now, the thing is, the picture is not going to remain the same over the next 20 years. Things are going to change drastically. So if you look at the picture for 2040, as predicted by the BP Energy Outlook, it indicates a reduction in coal and oil percentages. I mean, it's still 50% or more, but it's a reduction from our current needs. Whereas it shows a huge increase in the renewables. So if you look at what's going to happen in the next 25 to 30 years, the overall consensus is that the fossil fuels will continue to remain the most dominant source of energy, all right? But the share of coal and oil is expected to reduce. Here, as per the prediction of BP Energy, they're expecting 5% reduction for each, but it could be higher depending on how things work out in the next 10 to 15 years. There is, however, a very clear shift towards gas. So we're moving. So if you look at the gas percentage, this was 21% back in 2013, and in the next 20 years, we expect this to increase to 24% at least, or even more, right? And this is a very clear shift that we are seeing, and this shift is mainly because natural gas is a less pollutant fuel as compared to coal or oil. It produces less CO2 per unit of energy that it produces. So that's the simple reason for the shift. Well, in general, all fossil fuels are going to produce CO2, undoubtedly, but we got to pick and choose the ones which produce less CO2, right? Because we cannot change things immediately. Things are going to take some time. Now, apart from that, the big news is, of course, the renewables. Their share is going to grow rapidly in the next 20 years, at least by 500% or even more. As per the prediction of BP Energy Outlook, they're showing 5% energy needs coming from renewables. But we need to take this with a pinch of salt because this prediction was done 7 years back. And things have changed rapidly in the last 5 years with the rapid decline in the prices of solar photovoltaic panels. And I would say the share for renewables is going to be at least 5%. It surely is going to be more than 5%. There's no chance it's going to be less. So that's the biggest change that we're going to see. Apart from that, the hydro is more or less going to remain stable. There are, of course, controversies with regard to the actual benefit of hydro projects. So they have more or less stalled across the globe. On the nuclear energy front, we are expecting a steady growth. It's not as rapid as renewables, of course, because nuclear plants tend to be extremely costly. But we still expect a little bit of a growth, and they will capture about 7% of the energy needs. Now, the reason nuclear makes sense despite all its drawbacks is simply because it does not produce any CO2 during the energy production. The only CO2 that's produced in a nuclear power plant is during the construction of the power plant itself. And that primarily has to do with the fact that our current construction methods, they utilize a lot of cement, which produces CO2. So once you have built a nuclear reactor, nuclear power plant makes a lot of sense. Of course, there's also the problem of the waste, and that needs to be tackled. So if you look at all the different energy sources that are available to us, renewables are the ones that are going to take a huge share in probably the foreseeable future. But at least in the next 20 to 30 years, they're going to grow very rapidly. Now, the motivation for the transition from fossils to renewables has always been there. It's not something that became important in the last, let's say, 10, 15 years. The only thing has been the motivation. The motivation has changed drastically about why do we need to change away from fossil fuels? Why do we need to move away from fossil fuels? Now, if you look at the crude oil reserves across the world, this provides us a very good idea about why people have been trying to move away from fossil fuels. All right. So this is the map showing the crude oil reserves, and the black indicates the countries with 200,000 plus million barrels of oil: Saudi Arabia, Argentina, and Venezuela. Sorry, and these are the only two countries that have such huge quantities of oil. And then you have some countries in dark brown, such as Canada, Iran, and Iraq, with 200,000 million barrels of oils, and the rest of the oil reserves are distributed around the world. Not very uniformly, though. You can see there are countries which almost no oil, right? There are a lot of countries in Africa, a lot of countries in Europe, and the simple reason is that the simple reason for the governments trying to make a change is energy security, right? So energy security was one of the earlier reasons why we wanted to make the change, and it's pretty obvious from this plot. So energy security as a reason remains the concern even now. It's just that things were not feasible or economical enough for us to move away from fossil fuels. Now, apart from the energy security part, which is an important concern, the other important concern was the fact that we're going to ultimately run out of oil, or maybe we are going to run out of oil in the next maybe 10 to 20 years. And these fears have existed for, as long as oil became important. There were, if you look back into the history, you can see news articles, research papers published even in the 1980s, where they were talking about oil, about the world running out of oil within the next 20 to 25 years. And we are now 40 years ahead from that. We are in 2020, and we know we are nowhere near that point. Okay, so the question is, how far are we from this potential disaster point where we will run out of oil? So this graph right here shows the reserves to production ratio in years, right? So here 150 basically means that we have 150 years worth of oil still left in terms of the reserve. Okay, so if you look at this graph, this is the situation for 2019, and you can see across various regions of the globe, we have at least we have 30 plus years of oil left, and in the major producers such as the Middle East and South and Central America, we have easily 85 plus years of oil left. So that's still a lot of oil. And the thing is, if you look at the historical overview back from 89 to 2020, which is shown here in this plot, so it's showing that the curves have more or less fallen pretty slowly, right? Or they have either remained constant, such as the one shown here for the Africa curve, right? And in some cases, they have actually grown rapidly, okay? Such as the one shown here for the green, depicting the sudden increase in the oil reserves in Venezuela that simply came up, that became viable because of improvements in technology. So the simple picture is that we have been worrying since 1990 that we are going to run out of oil in the next 20 years. but the oil reserves to production ratio has more or less either remained constant or has dropped down so slowly that we have still enough of oil left. So the consensus now is pretty straightforward. It's simply that we don't have to worry about us running out of oil in the near future. I mean, yes, it's a concern. We will surely run out of fossil fuels, but it's going to take at least 100 plus years. So it is an issue, but it's not a very short-term issue. It's a rather long-term issue, and we have enough time on our hands to fix this. Okay, so this was the initial motivation why people started looking at alternatives to fossil fuel. But if you look at what has happened in the last 20 years, a more pressing issue is related to global warming. Now, this plot here shows the global mean surface warming temperature on the y-axis versus the years on the x-axis. And so here we have initial data till about 2018, which is shown in this black, and the rest are all predictions. Now, we know for sure that all the fossil fuels that we have burnt over the years have created or have increased the CO2 content in the atmosphere, and that certainly is bad for global warming. This is something that was debated in the 90s and early 2000s, but it's an established fact now. There will still be climate deniers, but more or less everyone agrees that this is an issue, and this is the issue that we need to solve for now, right? Now, if we allow the global warming to exceed 2 degrees Celsius, which it will surely do if we do not change the way energy is generated and it's consumed, then, well, we are actually going towards a pretty catastrophic scenario, because a global increase of 2 degrees Celsius would mean a lot of changes in terms of the water cycles, in terms of the melting of the polar caps, and in terms of the water levels in general. It's going to cause more flooding, more extreme climate. So that's certainly a scenario that we would want to avoid it as much as possible, right? So now there's no simple solution to that. We surely need to reduce CO2 emissions, and the way it's going to happen is through a variety of means, right? There are several ways available for us to reduce the CO2 emissions, and there's several sectors in which we can target, and the easiest target would be the one which are the bigger, which accounts for a huge share, and the transportation sector is one which accounts for a huge share of the CO2 emissions, which is why we are seeing a huge push towards electric vehicles, electric transportation in general across the globe. Now, before we look at the alternatives and how far the alternatives have progressed, let's quickly look at why have we been fixated with fossil fuels for such a long time. So why do they still dominate the market, and why do we say they will continue to dominate the market in, let's say, the next 20 plus years? So a simple reason for this is the fact is that their energy density is very high. So this figure right here, it shows the energy density for natural gas, gasoline, wood, coal, charcoal, and also for lithium ion. So here you see lithium ion is a tiny dot. Its energy density is about 100 times smaller than the energy density for gasoline. So the reason we have been sort of hooked onto these fossil fuels is because of their very high energy density, and the fact that these are all liquid fuels. They're very easy to handle, they're very easy to transport. And when we talk about energy source or a fuel for meeting our energy needs, we need something that has very high energy density so that it has less transportation cost, and it also should be easy to handle, should be easy to transport. If you cannot transport energy, you're going to have problems in making use of that energy by itself. All right. And although these are the reasons which have allowed natural gas or fossil fuels in general to capture a large market, a large percentage share of the energy market, it's not going to remain the same in the future, right? I mean, if you look at the history, we know for sure that we have always made energy transitions to better and cleaner fuels, and energy transition is not a matter of if it's going to happen, it's a matter of when it is going to happen, right? It is imminent, it is happening right in front of our eyes, and it's just going to continue happening even faster. So if we look at the historical overview, if you go back and look at how energy sources or the fuels have changed over the last 200 years, we see a very clear shift towards fuels which have more energy density and which in general are more convenient to use. Okay, so let me show that to you graphically with the help of this plot here. So this is of course showing it for US, but the same scenario sort of plays the world over. Okay, so this is showing the percentage of the energy contribution from different fuels, okay, on the y-axis, and the years are shown on the x-axis. Now, if you look at it, back in the 1970s and the 1800s, the primary fuel that we used was wood, right? There was absolutely nothing else. Wood was good enough to meet all our energy needs. I mean, there at that point of time, our energy needs were also pretty basic. It was just heating, okay? And around 1850, we started to move towards coal, right? Because coal was something which had better energy density, okay? Meaning you'd had to use less quantity of fuel in terms of kilogram to get the same amount of energy, and it was also much more convenient to use. So you can see this gray part coming in here, showing the shift towards coal. Of course, the shift is small at first, and then it goes to larger in 1875, and in 50 years' time, coal is the major player. It has captured all the a majority of the market of the majority energy market. However, at this point of time, we start seeing some parts of hydroelectric and petroleum coming into the picture. Again, as you can see, these are pretty small. But over the next 100 years, you can see that the share of coal has gone down drastically. Wood is completely out of the picture, right? It's just used for recreational purposes, if you want to think about it, for bonfires or something. It is not being used to produce any energy anywhere. And the energy market share as of 2019 looks a combination of coal, petroleum, and hydroelectric is here, and natural gas in the US. And you can see that natural gas and petroleum have taken a tiger share of the energy market. And if you go back 100 years, you can very clearly see this transition that has happened from wood to coal to petroleum, right? And this transition is a very clear pointer to how the fuels of choice have changed. We have always moved towards fuels which are cleaner, okay? So if you think about natural gas, burning natural gas is much cleaner than burning wood. Anyone who has cooked food using both these fuels can testify to that. So we have always moved towards cleaner fuels, and this progress towards cleaner fuel is not going to stop. In the next 100 years, this picture is going to look very different. I'm not saying we will not have fossil fuels. We will surely have fossil fuels. They're going to take a small part of the pie, just like coal is taking a small portion here. But we are going to have a much more varied distribution here with solar photovoltaic, wind energy, and even biomass coming into the picture. Now, what kind of energy sources we have? Well, it's going to depend on the geographical location and this kind of resources each country has. So this is something that surely is going to happen, and it's a matter of the rate at which it's going to happen. All right. So the question is, what is the future of energy? Now that we have established that we're going to move towards renewables, more or less, how does the future of energy look like? Is a change happening only in the energy production side, or is it an overall change? Okay, so let's look at a couple of slides to understand that bit more. So the overall picture is now to move towards electricity and to basically use different fuels to produce electricity, and then ultimately use electricity to transport energy. Right? We are not the idea in the future is not to basically be using any fuel per se to transport energy. So if now again going back into history, before electricity became more widely available, our energy needs, or in terms of light or heating, were met by burning candles, wood, or kerosene lamps, right? And this started to change as we moved towards fossil fuels, the development of electric power plants, and we have sort of moved away from this candle into these in this new generation of devices which are more efficient, right? So we went from candle to a light bulb, which was good, but not efficient, and then we have moved towards LEDs. So you can see a clear transition that has happened, and it has happened in the sense that we were burning fuel to produce the energy that we needed right in front of our eyes, but with the move to electricity, this burning of fuel is not happening in front of us. It's happening in faraway power plants. And what we get is the transfer of energy through electricity, which is simply an energy carrier. And what has happened over the past 20-25 years is that we have started to make more efficient use of the electricity. Okay. Now, electricity makes sense because I mean, you can create electricity using various means. And the overall picture of tackling climate challenge is basically to electrify everything, right? Electrify everything as much as possible, and that's the reason we sort of see electric cars like Tesla coming into the picture, and even Airbus and Boeing are starting to work towards creating hybrid aeroplanes. And the simple idea is that the transportation sector has been working quite a lot on this in this region, simply because that's the most visible sector, and it contributes to more than 30% of the CO2 emissions that we see across the globe. Now the question is how much of it is, so we know for sure that we're going to generate electricity, but what all sources are going to be used, right? So for now, we just make use of coal power plants in India, for example, and we don't burn, let's say, for natural gas or oil. That's too costly to burn, but it's mainly coming from coal power plants, hydroelectric dams, and so on. So the future of energy, electricity, is going to require a combination of different technologies. And in India, we're moving pretty rapidly towards solar photovoltaic and wind. It's also going to require some amount of waste to energy and the solar CSP to meet our energy needs, right? Each of these technologies has their own advantages and disadvantages. And the future is not a simple, the solution to decarbonizing the electricity sector is not a simple bullet point saying that, okay, this is one solution, it meets all our needs. No, it's not going to happen that way. We're going to need a variety of different resources to meet our ultimate needs. And among the four technologies that I'm showing here, solar PV is the one which is growing the most rapidly. Okay, so apart from the way we generate electricity, the other thing that's going to change is also the way we transmit or basically transfer energy, right? So in the past, because of the nature of the power plants, which are mainly thermal, nuclear, or hydroelectric, which are pretty huge, so the nature of generation was that we would have a centralized power plant, and then you would distribute it across cities, across towns, through transmission lines and substations and so on. So it was a monodirectional distribution, I mean, in which is happening throughout, and it was a centralized source. So this is the electricity network that we have currently, and this is what most people call as the past electricity network, or something that's going to change. So apart from the way we are generating electricity, we're also going to change the way we transmit electricity. So the future electricity network is more, it's going to be decentralized and bidirectional, in the sense that everyone who has enough land can set up a solar photovoltaic farm, right? You can set up solar photovoltaic panels on your roof. And it's also going to be moving towards wind turbines, right? Of course, wind turbines require a lot more space, but you could establish these in regions where we don't have traditional power plants. So it's going to be decentralized. It's not going to happen. The energy is not going to come from one given source. It's going to come from multiple sources. And the energy transfer is going to be bidirectional, in the sense that if you generate excess electricity in your homes, you'll be able to transmit it to the power plants or to the grid in general. And this, the bidirectional part has already started, right? In India, in a lot of states in India, we are already starting to do that. You have bidirectional meters where you can, connect the solar panels to the grid and transfer the energy. So this is something, again, the future electricity network is something that we are already moving towards, right? It's something in the works. We have not optimized it, but this is already a work in progress. Now, if you talk about how quickly this is going to happen, well, let me show you these projections for the solar photovoltaic. And I'm using solar photovoltaic here simply because this is the solar photovoltaic are basically the dominant renewable energy technology, which is growing rapidly, right? All others are growing, of course, but this is the one which takes the huge share, let's say, right, of solar. And this plot here shows the cumulative solar installations on the y-axis. And although showing photovoltaic plus the concentrated solar, which is solar thermal, photovoltaic contribute to 99% of this capacity. So you can assume it to be just photovoltaic, all right? And on the x-axis, we have the years. So here, I have some dotted lines with along with the year written at the bottom. So this basically shows the projections of IEA, right? So this is an international energy agency, which basically makes projections every few years on what they expect the photovoltaic share to be in the electricity market. They just don't make it for photovoltaic; they make it for others as well. But here I'm just showing it for photovoltaic, and as you can see here, this was the projection up to 2013, 2006, right? In 2009, they increased their projection. 2012, they increased it further, and they have been increasing it throughout. But the dots here are the ones that matter. Dots are the observed ones, right? This is what has actually happened. The lines are simply the projections. And what has been observed in terms of the uptake of solar PV is a huge rise from 2010 onwards due to the sharp decline in the prices of solar photovoltaic panels. And we are in year 2018, we are somewhere here, about 500 gigawatt peak power is coming from photovoltaic panels. And you can see that even back in 2011, we could not predict that, right? 2011 prediction for 2020 is about 200 gigawatt peak coming from photovoltaics. But we have far exceeded that. We have even more than doubled that, right? So the projections have always fallen back, and we're growing at a rate which is much faster than what we have projected, even as far as 5 years back. So this is a transition that's happening. It's happening fast. How fast? Well, our projections can only give us an estimate, but we can expect to see drastic changes in the next 20 years. So now, considering all these huge transitions that are happening in the energy domain, it's really important for us to ask what role can we play here? How can we make our students ready for this new age where a lot of these changes are happening? And it's probably a good time to ask, what is the future of teaching and learning as well, right? How do we learn? How do we teach students? How can we make them better engineers, better scientists, better salesmen, for example? Everything that, how can we make them better and more tuned to the new change that's going to happen in the next 20 years, and whose part they're going to be, right? So I'm going to show you some of the strategies which we have used here at KFUPM, and also some of the strategies which are used across the world to improve student retention and to improve the course learning outcomes, to improve basically the way students learn the material, right? So if you want to classify all of them, we can sort of broadly put them under the active learning methods. And there are several active learning strategies that have been used across the globe. I'm going to list some of them, and I'm not saying that all of these need to be implemented. I'm going to share about which ones can be implemented soon, which one will take more time, and how do you go about doing it. All right. So one of the most common method that's being used across the world, not just in universities but also in schools, is to move towards this mode of inquiry-based learning, where instead of transferring the material in terms of giving a presentation or just coming and telling them what needs to be done or how things are done, we focus on solving questions, or you evaluate scenarios, or you do case studies to explain how a certain problem needs to be solved. So again, the bigger picture is that you're transferring knowledge, but you're not transferring knowledge through lectures. You're transferring knowledge by asking students to solve questions. And here, this is something that has worked out very well in terms of improving student retention, right? So this is one technique that can be used. Of course, it's a completely different way of education. So it's not easy to move directly onto it, but we can take some aspects from it and move on, catch on to those and make a transition slowly towards a more better learning method. The other method that's even more, let's say, drastic is on project-based learning. So here, you want to cover a certain material. Yes, you want to do that for sure, but you're not going to do it through lectures. What you're going to do it is you're going to come up with projects and allow students or help students along the way as they solve the projects, right? So here, the difference between inquiry-based learning and project-based learning in really simple terms is the fact that in project-based learnings, you're just focusing on one big project or maybe a series of small projects where students solve the projects and learn the material. In inquiry-based learnings, it's broken down into even smaller segments, but the purpose is basically the same. You are involving students and you're giving the onus is on the students to learn, right? You're giving them a challenge. You're giving them, all right, let's say we want to come up with, we want to design a solar panels or a solar park to meet, let's say, 100% of the energy needs of my university. How am I going to do that? what are the ways that I can do that. So you can have projects, for example, like this, where the student goes through the learning process, looks at how it needs to be done, and then eventually learns the knowledge that you wanted to teach them in the first place, right? So the whole idea is to shift the way the transfer of information happens. Okay, you're surely doing the transfer of information. You are achieving the course learning outcomes in terms of covering certain topics, but you're just doing it in a very different way. So these are two techniques which are broadly, I mean, there are a lot of techniques within them which are broadly being used across the world to improve the way students learn, improve their skills, improve their confidence in terms of how much they know and how much they can use. Now, we can also bring out some of the other smaller versions of these, which can help us improve rather quickly, right? So one concept is about think, pair, share. The concept is pretty simple. So what you do is you ask your students a question, and you allow them to think you give them probably a minute to think, and then you ask students to pair, right? To form pairs of 2 or 4 students, and then they're supposed to discuss the solution among themselves before sharing it with you. Okay, so the whole purpose of the strategy is to improve teamwork, improve communication skills, and to help students learn from each other, right? So if we just had the pair share part, the students would not have the opportunity to think by themselves. But here we're giving them enough time to think by themselves and then move on to the pair share part, which is a very important part of the learning process. And this is something that can be implemented in a rather easy manner. It doesn't, I mean, it's going to take probably 5 minutes of your course time, but it's worth it from the point of view of student engagement and the way they are able to grasp the material. The other very common strategy that's being deployed across the globe is about the flipped classroom concept. Now, if we think about the classroom, what we do is we teach them, we give them lectures, we transfer information, and then we give them homework where we test whether they have understood the information. So the idea here is to basically flip it, right? So we don't want to transfer the information in the class because what we are saying is that maybe you can replace it with a recorded lecture. Maybe you can give them a reading material. You can tell them, okay, there's this video on YouTube from maybe MIT, from IIT, which covers the same material. Okay, let them go through the video and understand that, and you test their understanding by solving problems within the class, right? So this is basically essentially flipping the classroom and doing classwork as homework and doing homework within the class, right? Now, the advantage with this is that students get to look and study from a different perspective, and you get to test them and see what their concerns are in the classroom. You will see where they are failing, right? Now, if we compare it to the traditional scenario where we teach in the class and then let them do homework, we know, I mean, irrespective of what happens, we know for sure that there are only, I mean, in a given class of 60 students, probably 6 students solve on their own, and the rest of the guys, they just share it among themselves, right? Some people understand the solution, some people just copy it. So this is something that we want to change, right? And we want everyone to have an understanding of that. And if they're feeling, if they are not able to do that, they should very clearly be visible to us so that we can help them. So this is a big change that's happening. And again, this is not something that you want to implement throughout the semester. You want to try it out for a couple of topics which you think are easily available on the internet or whose reading material is very easy to understand, so that the students do not face a problem here. Okay, so these are a couple of strategies which can be used to improve the entire learning process. Now, I just want to give you a couple of bullet points to basically solidify why should we move towards active learning, right? There are a lot of advantages. I'm just going to point out a few of them. One is certainly it improves retention of the material. It helps the student understand the material a bit more, and they're in a better position to make use of it. It improves their communication skills as they discuss among themselves and work more on it. It also has typically more assessment components in the sense that you can give them project work, and you can also ask them to make presentations. And it's a more better way of giving the students a well-rounded personality as well as a better transmission of information. Of course, it requires teamwork, and we know that in the job market, teamwork is extremely important. Nothing is achieved by students by themselves. Even when they work, they have to work in teams. So this is a culture that we want to encourage from now onwards, because students, they throughout their schooling, they have been through a situation where it made it made no sense to share the solution with others. If they shared their knowledge, there was a chance they could lag behind. The other guy could be, the first in class, and that's something that, in general, our society does not accept. So, but that some completely is out of line with what's required in the workplace. So we want to encourage teamwork, and we want to encourage it as much as possible, and from the university itself, in as many courses as possible. All right, so I'll just wrap up. I think I have a couple of minutes left. So now, in terms of how we can improve the learning outcomes, apart from the ideas that I've shared, well, we need to focus on connecting the material that we teach to real-world applications as much as possible. And this is a key part right here, right? We tend to focus on covering a material, on discussing a topic, but a very important part is to teach them why should they learn that? What is the power? How does it help, right? That part is very important. If we do not cover that, then the students are not really tuned into understanding what they should learn, and it doesn't really help. They are not able to understand even the power of it, even if they have the knowledge. So this is a very important thing that needs to be covered, and we need to sort of increase student participation either through a lot of questions within the class or by conducting polls. Now we also need to give them time to think and respond, because typically when we ask a question, we sort of see who's raising hand first, and then we give him the chance to answer it. Now this is a common practice, but it doesn't really help again, because what happens is that you just have the same student or the same set of students answering you throughout the semester, which is not what you want. A better strategy is to use polls. Everyone has mobile phone, everyone has internet. Make use of polls on Teams or on Google, and let all of them participate. And we
Sorry
can
for
also
interrupting. Awad sir, 1 second. So can we have some questions also, like in play, because none of the participants ask questions. So if you don't
All right.
mind,
I'll just
can
complete
spend 2
this.
minutes? I don't mind. Yeah, after completing this, we can just have it, sir. I don't like, we don't extending the time of 5-10 minutes. Not an issue, sir.
Okay. No, I'm just completing this slide. So
Sure.
that's it. This
Thank you,
is
sir.
the end of my presentation. Yeah, thanks. So lastly, I mean, it's simply about encouraging students to teach among themselves. Sometimes it helps to hear from someone else teach them same topic in a different way. And flipped classroom or think pair share provide opportunities to implement the strategy in a very easy manner. And lastly, I would strongly encourage to think about incorporating project work and as many courses as possible. For senior courses, like in the final years, try to give at least 30% for project work, because it gives them all the skills that they need in the industry. It helps improve their communication skills, teamwork, and also it helps them understand the power of the subject, helps in subject retention. So, well, that's it from me. Thank you. I'm all here for taking questions.
Unmute and ask the questions, please. Any questions, participants? Anuradha ma'am, any questions?
No, ma. Thank you.
Sir,
Any questions from any participants?
hello. You talked about active learning and some of the methods you can implement. What are the practical difficulties in following this kind of active learnings compared to the existing conventional things?
Yeah, thank you very much. That's an excellent question. So, I mean, when I started implementing this, especially the flipped classroom concept, the initial concern was the fact that, I cannot do it for the entire course, because, first of all, as humans, we don't like change, right? Students also do not like a huge change to happen. Now, the other thing was implementing the flipped classroom requires some practice. It requires a lot of effort from our side.
Yes.
So, the way to implement this is probably by just doing it for one topic. So, for example, I teach a course on thermodynamics, and the material on, let's say, refrigeration is sort of covered in high school physics, and again we teach it in the second year. So what I did was to just select that one topic, and I made a recorded lecture on YouTube, shared it with them, asked them to go through it, and did a quiz at the end, at the beginning of the class. So this way I ensured that the students basically went through the material. And then basically I gave them a couple of questions to solve, and divided the class into four members, four teams of 4 members. And the idea was they were trying to solve it by themselves. They were getting all sorts of questions which they would not normally get in a class, because they just see the solution and they think, okay, it's pretty easy to solve. So, I mean, in terms of the difficulties, well, when you do it initially, there may be a situation where things don't go according to plan. So you have to sort of start slowly, but keep improving it every semester till you're more comfortable with doing it, and till you have also taken student on board that this method works. So yeah, these are the difficulties that I sort of faced initially. Let's say I think in a class of 30, there were probably 1 or 2 students who were not so comfortable with this, but almost everyone took to it instantly. So not much resistance from the student sides, but yes, you still have to sort of put in a lot of time before implementing the strategy.
Yeah, so that's why. How do you find that much of time to spend on preparing all this kind of classes? It requires intensive preparation for a long time. So
Yes,
that
absolutely.
how did you manage? You have been given enough time for this, or how did you manage the timings of preparing for classes for this?
I mean, apart from the preparation time, this also tends to take. This also tends to take slightly more time in covering a certain topic, maybe 10 to 15% more time. So now, the way, as I said, the way I did it was I started by doing one topic in a semester. So I removed 2 lectures and replaced them with recorded lectures, and I used the class time to solve the problems within the class. So I did not do it initially for the entire course, and taking out time for this was, I mean, I probably needed a day or two, I sort of did it before the semester. So you have to do it slowly, right? And it's going to happen over the years. So if you're teaching, let's say, the same course every 2 years or something, then if you start doing it on a topic by topic, maybe just replace one class with a flipped classroom and implement this. So you have to sort of do it slowly. It doesn't take much time. I mean, I was able to do it with in less than 2 days. The first flipped classroom implementation. It took less than 2 days of my effort to actually do it properly. So yeah, I would just recommend that try doing it in small parts. And yes, we are all extremely busy. I completely understand that and empathize. But I think little bit doing it bit by bit always helps, and it ensures that we are able to make progress while teaching, let's say, the same material over the.
Did you evaluate the student at the end about this intensive preparation which you imparted to them? Is it really valued at the end semester examinations, or it is not much of value at that time?
Yeah, no, another excellent question. So yes, we did a survey, and I mean, this was done not just in my course, but there are also a lot of other courses where we are implementing the strategy, and the overall feedback was very good. We saw students performing well in the exams as well, and in terms of the feedback, if I recall correctly, I think about 90% of the students were either happy or very happy with this change, and they said it improved their retention. There was probably about 5%. There were about 5% of the students who were not too happy with this, because they were forced to do homeworks in the class, and these were the guys who typically copy from others. So they don't like to work. So I mean, you will always find them, but the vast majority were extremely happy, because they felt that they were able to learn a lot more, and they were able to discuss their questions within the class, which normally does not tend to happen.
Okay, thank you.
You're welcome.
Any more questions, participants? Participants, any more questions? Okay. Awad, thank you very much for the time you have shared with us. And I hope the participants all had a good session.
Yes, thank you very
Awad,
much.
sir?
It was a
Yeah, thank you so much, sir.
It was a pleasure to present.
It was very pleasant. Yes, same with us too, sir.
Thank you.